Hey, everybody. Happy last day of summer, August 31st. Welcome to AI Exchange. We have an awesome presentation by Vishal Asnani today. We're going to be talking about detecting deepfakes. But first, I want to welcome everybody in the community and make a few announcements. One, I want to let you guys know that this is your community, and I'm really looking to you guys to help me source the kind and tenor of content that you want to see. So if you would like to be a presenter like Vishal, please reach out to me. Hey guys, so sorry for that little bit of technical difficulty. So thank you so much. First, I just want to say, please, this community is all about you. I want to hear from you. I would like for you to present for us. So please reach out to me if you have any ideas. Also, we would love to see you at TransformX. It's happening October 19th through the 21st. Registration is free, and Janie, our exchange coordinator, is going to drop the link in the chat right now. Last but not least, I want to remind you that the last Thursday of every month in Scale's SF headquarters, we have an in-person meetup. So if you're really dying to meet up with your peers and grow your connections and just be around humans after many years of COVID and being isolated working remotely, please come and join us. The next one is Thursday, September 29th, and I will be there in person. And I want you guys to know this will be recorded. So if you miss any part of it, you can find it on AI Exchange platform and replay later. Now I would like to introduce our very special guest, Vishal Asnani.
Hi, Natalie. Thank you for
Hi,
your
Vishal.
presentation. Yeah.
Thank you so much
How
for
are you?
being here.
Yeah, my pleasure. How are you?
A little bit about Vishal. Vishal is a PhD researcher at Michigan State. He's quite accomplished in publishing two very significant papers, one of which proactive image manipulation detection he'll be presenting for us today. But there's also some really exciting work that hopefully we'll be hearing from him in the future about detecting regenerative models and actually being able to figure out the source of the deep fake. So hopefully we get to hear from you later about that, Vishal. But if you
Definitely.
don't mind, well, I just want to let the community know that you and I met at CVPR earlier this year at Scale's coffee stand. And Vishal was very warm and kind and excited to come and present for us today. His paper, Proactive Image Detection, Manipulation Detection, was actually accepted by CVPR. So, Vishal, I will let you take it away from here if you want to introduce yourself.
Sure. Thank you, Natalie. Thank you for the kind introduction. So, hey everyone. So, I'm a third year PhD student at Michigan State University under the guidance of Dr. Xiaoming Liu. So, my my research interests basically include deepfake detection and manipulation detection as such. So, yeah, I guess we can. Let's hope that you like my work and yeah.
I'm sure we're going to like your work. So I'm going to go ahead and add your deck to the screen now. And I'm going to remove myself, Vishal. So I'm just going to let you take the presentation away from here. But I want to
Okay.
let our community know that for the very first time, we're experimenting with a new methodology for engagement, actually. So previously, you guys would actually just chat your questions in the live chat. Today, after Vishal's presentation, if you look to the left side of your screen, you'll see several different lists of words, of activities: live, agenda, roundtable, match. And at the end of the live stream, Vishal and I are going to jump off of the live stream. And if you drill into the agenda, you'll see that you can join the roundtable. And in the live Q&A roundtable, you'll actually be able to meet with Vishal, not in person, but face to face, and ask him your questions. And we're hoping that this will be an opportunity for a deeper, more meaningful engagement. So I'll remind everybody at the end of the presentation how to get there. But just wanted to give you a little bit of a heads up that the Q&A is going to go down a little bit differently today. All right, Vishal, I'll let you take it away.
Thank you, Natalie. So yeah, I hope you can you're seeing my slides. So I'll be presenting my work in CPR 2022, the proactive image manipulation detection. I would like to acknowledge my collaborators, Dr. Shi and Dr. Tal Hasno from Meta, and Dr. Sijia Liu and Dr. Xiaoming Liu from Michigan State University. So yeah, let's jump into the paper, I guess. So yeah, so coming to the problem definition. So what exactly are we solving here? So prior methods, we can tell that we can actually think of them as like a passive detection, which basically takes an image X, pass it through a generative model, and manipulate the image. Let's say here in this example, it's manipulating the color of the color of the hair, and we basically apply some black box algorithm of detection, and many of times we have seen that it actually fails, that the algorithm tells that the fake one is also a real image. Now what we are planning to do in this paper is that we are relying on on the concept of image encryption, which basically adds a particular template onto the image to uh, basically protect it from any further manipulation as such. So let's say if we add the S template here to the X image, and we get a template protected image. Now this template protected image, when it passed through a CAN model like in the first stage, but the only change is that this is the protected image here, it will the algorithm would basically be able to tell that what is real and what is fake image. So the idea is to basically improve the manipulation detection by adding this particular template in the for on the real images. Now we have seen that we are like usually now in in the community for defect detection, we train on manipulated images by 1GMs, and we basically want to test on unknown generative models. So by unknown, I mean that they are not seen in the training, and but like there are n number of models that are coming out there every day, so we cannot just go ahead and train on the images for every model. So we should be able to design a generalized method to catch all the fake images. So basically, if we have a real images, we should only train on like 1GM, and so this is what our proposed framework will do. It just trains on 1GM and to estimate the template. With now this template will be added to the real images, and it can be tested on different unknown generative models out there, and basically for everyone we can do generalized image manipulation detection. So now there are various challenges that we can face on for this kind of problem. Basically, we are saying that we are learning a template, but there is no ground truth, or we don't know how the template will look like. So how can we basically add this template if we don't know how it looks like? So that is one problem that we have to basically find a template in an unsupervised setting. So because there is no supervision for supervision for optimizing or recovering the template. And we also need a multi-template set uh, because you can think of it like the template is kind of like a one key to the lock. Now if we have like one key, attacker can easily reverse engineer it and again remove the template from the real images. But if we have like let's say 1,000 templates out there, then it will be very difficult for any attacker to reverse engineer these many templates. And the fourth is that the basic image editing operations like blurring of the image or applying some compression or some filters onto the image, it can deteriorate the performance of the image detection. So without wasting time, let's jump on to the framework. So basically, we have two stages into our algorithm, that is the image encryption and recovery of the template. The image encryption, basically, we initialize a template set which has n number of templates and randomly initialized. Now we basically choose a random template from the set by a random number generator to select that template and add it onto the image. We control the intensity of this added template by a hyperparameter m. So I'll come to the ablation of this later. So we add this template to the real image and get an encrypted real image. Now this encrypted real image, like I said, it will be passed through a GM to produce a fake image, and we basically will have an encoder after that to recover the fake and recover the real and the fake template that is added. Now and we basically use the cosine similarity of the recovered templates with the original template set to perform the real fake classification. The intuition is that for the real ones, we should be able to recover the exact template that was already added onto the image, but for the fake ones, it should not be the case. So for the real ones, we will have a cosine similarity of close to 1, and for the fake ones, we will basically have cosine similarity of 0 between the real and the added template. And we basically apply various loss functions to learn this optimal template. I'll come to this loss functions in a bit. So coming to the, like, let's say, just to give you a glimpse of what exactly is happening, we have a real image, we basically have a template, we encrypt this real image, and you can see that there is no there is no uh, uh, you cannot distinguish between this encrypted real and and the real images because of the low magnitude of the template. And it will pass through different GAN models to produce the fake images, and we basically recover these fake images, recover the fake and the real template by using our encoder. So coming to the constraints that I told you about, the 5 constraints that we are using to guide the network. So while talking about the challenges, I told that the template, we don't know what the ground truth, what the template looks like. We have to basically let the network find it based on certain constraints that we want that we will impose on it. And so the first constraint will basically be the content independent signal loss. So like I said, that the algorithm should be generalized to many different generative models with different domains. So it can be either the face images or outside scenery or buildings or anything, any other picture that is out there. So we basically want to remove the content dependent information from it. So use the Fourier transform to apply a high pass filter to just encourage that the template should have high frequency information to it, so that we don't get any content dependent information in the template. The second is the magnitude loss. Like I said, that the template should be as small as possible. It should not deteriorate the actual quality of the real images, because the user always wants that this template should, like the quality of the image should be preserved. So we should have a low magnitude of the template. The third is that we have a set of templates. So basically we have S1, S2 till Sn. They are basically like different keys of the template. So each key should be different to each other, but serving the same purpose. So it is, so basically we will make S1, S2, Sn to be as different as possible. The fourth one is the recovery loss. So whatever template we are recovering from the real images, it should be similar to the actual added template. So S should be equal to SR, and the separation loss, basically the fake recovered template SF should not be similar to the added template S. So using these all 5 constraints, we train our network. So we choose syllabi HQ, 24K images of syllabi HQ for training. And for the GM, we choose STGAN for the training and produce the corresponding fake images to it from it. For the testing, we have around 15 different GMs, 16 different GMs to test on. Uh, the data set is quite diversified here with the face images, the facades, the edge to shoots data set, the LSM, the street, uh, that. So this basically tells us that our algorithm is much more domain independent and can serve the purpose of detection through multiple domains, not just only on the domain it is trained on. So, uh, so coming to the results, so we have we compare our results with the prior works of prior different works. Most state-of-the-art work was CNN generated images, surprisingly easy to spot, uh, authored by Shengyu Wang. So we basically see that we train on STGAN, and we test on on 3 different GMs, that is CycleGAN, StarGAN, and CoreGAN. So we can see that the performance of CycleGAN and StarGAN is more similar to AutoGAN, and the STGAN respectively, it's giving also the same performance. So if we choose only STGAN in the training, we were not able to beat the performance of the previous prior works. But when you incorporate AutoGAN into the picture, so we've basically achieved perfect average precision for all of 3 GANs. And you can see that there is a very high jump for GAN, because the architecture of GAN is very much different compared to CycleGAN and StarGAN, which have architectures similar to AutoGAN and STGAN, which are used in training. So that's why the prior work is getting around 100 or around 100 performance when used to AutoGAN, but for GAN it fails miserably. But our work is able to are able to detect the GAN images quite perfectly. So basically, now we are saying that we have a passive work. So we are all the prior works in image manipulation detection have been passive in nature. Now, but since our work is a proactive it's a proactive scheme. So is there any other scheme that is out there that we can compare our work with? So basically, if we see the Ruiz et al.'s paper on disrupting deepfakes, they basically add adversarial noise onto the image to protect it. And basically, after the protection, the output of the generative model will basically be messed up. And we are also basically kind of doing the same. We are adding an optimized template onto the image and passing it to the generative model, but we don't care if the output is messed up or not. Maybe the generative model is able to produce a good output image. Now, the main thing is that if we look at the performance of ours versus the previous work, we were basically more generalizable across all the 4 different GAN models: CycleGAN, StarGAN, GAN animation, and Pix2Pix, compared to the prior corrective work on image description. So this basically proves that our framework is much more generalizable and much more efficient in catching the fake images. So apart from using the 3 using just the three generative models, CycleGAN, StarGAN, and GAN. We also consider testing on various generative models. So you can see 12 other generative models, and we compare our work with the Wang's paper, and our work is, if you see, the average precision is has gap of almost 10%, which is uh, much more better than the previous work, and we have a better performance of a framework across all the unknown GMs. And yeah, the point to be noted here is that these all are unknown GMs, so the training algorithm doesn't see any of the generative models in training. So it proves the very crucial property of generalizability across deepfake datasets. So coming to the image editing operations, like I said in the challenges, so we basically apply image editing operations like blurring, JPEG compression, or applying both of them, and resizing, cropping, Gaussian noise. And we try our method on three different settings where we apply the augmentation either in training or testing, or only in testing. So for the first case, when we apply augmentation in training, we can see that the performance increased when the augmentation was applied, compared to the case where no augmentation was there. So this actually proves the basic machine learning point that if you augment different data, the algorithm becomes more robust to the specified task. Coming to the other two cases where the augmentation was only applied in testing or applied in training and testing, both of them. So we can see from the curves that average precisions in the first case basically are generally smaller than the second case because all the operations are obviously seen in the training in the second one, unlike the first one where we just tested on front blurred or Gaussian, not added Gaussian noise images. So uh, yeah, so so we again carry out ablation of the template strength and set size. So template strength, if you remember from my framework, the M parameter to control the intensity of the template. Now basically, if you increase the strength of the template, the image, it will be very easier to get it back because we have a lot of information of the template onto the image. But it will also increase the noise into the image. So the PSNR will increase if the templates if the PSNR will increase if the template strength is decreased, and it will make it harder to recover the template. But if we for the set size, if we increase the set size, we saw that we were able to gradually reach a upper cap on the performance, the 100% average precision, if we increase the set size. But if we have a set of around 50 templates, it is very hard for the algorithm to find all the 50 templates which are much alike with each other. So we can see that the cosine similarity also increases between different templates in the set. So again, for just a visualization of the template strength here. So we have the strength of around 10%, 30%, 50, 70, and 100. You can see at the 100% strength, the image has become much more noisier. However, we will get a good performance if we have a higher strength of the template into the image. So clearly, there is a trade-off between both of them here. So yeah, the image becomes noisy, and but if the strength of the template is increased, but the performance also increased, so there is a big trade-off that we have to choose here. Coming to the loss ablation study, so I showed you a few slides back 5 different loss functions: the magnitude loss, the pairwise distribution loss, the recovery, content independent, and the separation loss. So we basically prove the importance of each loss by removing every loss one by one from from the algorithm and seeing what's the impact in the performance. So for the first case, we remove the magnitude loss and see how the performance is varied. Same with all the losses. So we see that from all the 5 cases, if we remove any one of the losses, it deteriorates the performance of the algorithm. So it basically the performance is the red box. You have to compare with the performance in the nothing row, where we don't remove anything. That is the proposed framework. So performance in that is much more higher compared to if we remove any one of the losses. The second one is to remove the losses L1, L2, and L4. So the L1, L2, and L4 are basically used to directly optimize the template here. So if we remove all 3 of them, we are saying that we are just using a fixed template onto the to add it onto the real images. Now that will be a problematic situation because the algorithm won't be able to optimize the template for the final task of the image manipulation detection. So basically fixing the template are making the results first. So it is necessary for the algorithm to find the optimum template. And this also can be connected with the steganography techniques, where it uses just it we basically hide the same information on all the images. The thing is that it is not at all generalizable if the information that you are adding is not optimized. So yes, the optimization of the template is very, very necessary here. The third point is the removing the L3 and L5 loss, that is the recovery and the separation loss. So basically, in this case, we actually remove the encoder and just do a classification directly onto the images. Now that is also harming the performance, because having the encoder is beneficial because the encoder learns to see the data independent information in the template. But if we just have a normal classification network, it will overfit on the data that it is trained on. Like, let's say we take a face data like Syllabus HQ, so it will be overfitted on all the faces of the data. And if we test it on like say buildings data or some beach data, outside scenery, it will miserably fail on that. So you can see in this performance, the star GAN, which has the face data, it works pretty well around 98.24 average precision. But for cycle GAN and GAW GAN, where the data varies a lot, where the data domain is changed, the performance is miserable there. So having the encoder is beneficial and recovering this template is very, very important. So coming to let's say I said that we have a template set we have a template set with n number of templates. So let's say we just consider a case where we optimize a set of 50 templates. It can be now you can consider that we are adding the templates randomly onto the images. That is, I mean that I use the random number generator to randomly pick the template from the set and add it onto the image. But what if this random process uh, can be uh, uh, switched to some network which basically decides what template should be added onto what image to basically increase the performance. So if you basically add the best template which is able to identify that image onto the set, we can see that the variation here is with the it for the cycle GAN and star GAN, it doesn't vary a lot. But for GAW GAN, the performance is varying if we give the importance to selecting this template. Now, as I said, we basically used a template selection network to choose what template would be added onto the image. Now, the thing is that it gave us less performance. You can see on the third row, the network-based. Why was this? Because when you're training a network, then it when you're using it for when you're using it when you're selecting the template randomly, it gives importance to all the templates into the set. But if you are selecting a template based on a network, the all the templates are not getting optimized properly, which is basically uh, uh, the end goal the end the we are not achieving the objective of this to find the optimum template for everything in the set. So because of this, there is no because there is we basically get a worse performance. Now, I think the last study that I want to show you guys is that cross-encoder testing. So let's say we have a template set 1 and an encoder 1 and a with another template set 2 and an encoder 2. And you basically mix the template set and the encoder in this case. So you basically, after the training, we test it on template set 1 using the encoder 2 and template set 2 using the encoder 1. So we basically uh, use the three different initialization seeds for the template sets and encoders, and we test it using the cross. Test it on using the cross encoder template set to for the evaluation, and you can see that the performance is not varying much across all of the across all three GANs with uh, all three GMs with all the scenarios of the initialization seeds. So we can say that it's a stable framework, and we are basically achieving optimum set of template and optimum encoder. And if you use different seeds, then also you will arrive at that particular optima only. So the conclusion is basically we are proposing a proactive scheme for image manipulation detection, where we estimate a set of templates using certain predefined constraints onto the framework, and we basically have much better performance compared to the previous works. So yeah, I think this was the end of my presentations. We can switch over to the exchange forum to get on the call with for all the questions and everything.
Thank you, Vishal. That was awesome.
Yeah, thank you.
So exciting to see the full presentation versus the more condensed at CVPR. One quick question for you, and then I'll remind the audience how to transition over into the live Q&A. But
Okay.
how do you see proactive image manipulation detection methodology being mapped to the real world? Like, what do you think? What's the use case? Because I think that's what's on the rest of the world's mind that aren't necessarily machine learning engineers.
Exactly. So yeah, so the main idea of using the proactive scheme is that you add the template and it will help us to do the detection afterwards. Now it is very hard to add the template manually by every user. So ideally this template would be added when the camera of a user takes a picture or captures an image basically. So when the image is being captured, the template would automatically be added onto the image. So if a user then decides to publish apply post the picture to Facebook or any other social media, he can remain quite certain that if any fake image comes out there, then we would be able to catch it. So the deployment to the real world is still quite far, because it has to be added onto the camera designs, but it's still quite possible.
That is really awesome, Vishal. Congratulations to you and your team for producing
Thank
this
you.
awesome work that really does have real life implications. Just a
Thank you.
reminder for our audience then, we're going to do a live Q&A today, so we're going to transition to that in a moment. Please give Vishal and I maybe 20, 30 seconds to transition over or less. But if you look at your screen and you look to the left, you'll see the different words live, agenda, roundtable, and match. Once again, we're going to now drill into the agenda and join the roundtable if you would like to actually engage with Vishal face to face and ask him your questions. So before we do that, I just want to thank you so much, Vishal. That was really fascinating. It is really an honor to have you here today. And we're going to have this recorded and up so that people can continue to see it and share it with their communities, just in case they missed the live stream today. But it was really such a pleasure, Vishal. Thank you so much.
Thank you, Natalie, for organizing all of this. Yeah.
My pleasure. We'll see you shortly in the live Q&A.
Sure. See
Okay.
ya.
See ya.